So what we want to do now is continue our discussion of various orders of growth and domination. We've already seen with the examples that I've shown, right, we have very different meanings for the notation that f is dominated above by g compared to the notation for f is dominated below by h, compared to the notation that f has the same order of growth as some function L, which is that f is dominated above both by L and dominated below by L as well. And that's different than f is strictly dominated above by G. So let's jump into some more examples and see if we can't go through and show some more of the relations that we talked about previously. And the first thing that I'm going to do here is prove a lemma. And this is that n is strictly less than 2 to the n for all n in the positive integers. And we'll start with the first statement. We're going to do this a proof by induction here. If we start with our base case, this is to show that 1 is strictly less than 2 to the 1, which is just equal to 2. So this holds. You can also show that 2 is strictly less than 2 squared, which is 4. So this holds, and so on and so forth. So our inductive hypothesis will be that there exists an n in Z plus such that n is strictly less than 2 to the n in the inductive step. Will be to show that for all n in Z plus, if n is strictly less than 2 to the n, then n plus 1 is strictly less than 2 to the n plus 1. So we start by assuming that n is less than 2 to the n for some n, and we want to show that n plus 1, this implies that n plus 1 is strictly less than 2 to the n plus 1. So to show this, we'll start with our assumption, which is that n is strictly less than 2 to the n, and if we add 1 to both sides of this, we have that n plus 1 is strictly less than 2 to the n plus 1. And you can look at this and think about it for a second. And what we obtain is that this is also going to be less than or equal to 2 to the n plus 2 to the n, because 2 to the n will always be greater than or equal to 1. Actually, it would be strictly greater than 1 if n is greater than 1. Greater than or equal to 1. So this is the same thing as 2 times 2 to the n, which is 2 to the n plus 1. And so we've shown that n is less than 2 to the n implies n plus 1 is strictly less than 2 to the n plus 1. and our proof holds. And the reason that I went through and did this lemma is because now we can actually show the following. That n is strictly dominated by 2 to the n, where n is a positive integer. And the proof of this is relatively straightforward. We can use the inequality. Part 1 of the proof involves us showing that n is dominated above by 2 to the n, or n is big O of 2 to the n. And from the previous lemma, we have that n is strictly less than 2 to the n for all n in Z plus. So taking constants k equals 1 and c equals 1 as witnesses, as you remember, the domination relation requires taking these values, or certain values of a specific value of k and a specific value of c as witnesses. We have that n is big O of 2 to the n, or n is dominated above by 2 to the n. The second part of the proof, it can be done by contradiction. Similar to before. And I suppose I should at least go over one of these showings of the second part, because it is very important to kind of understand that strict domination is different than just regular domination. So we have to show that despite the fact that n is dominated above by 2 to the n, 2 to the n is not dominated above by n. And we'll do this by contradiction. So we assume that there exists k and c such that for all n, which is the domain of our function, if n is greater than k, then 2 to the n is less than or equal to c times n. So we're going to assume that there exists these k and these c, and if this is true, then that means that there exists k and c such that for all n greater than k, 2 to the n over n is less than or equal to c, or 2 to the n over n is bounded. But this is actually where the contradiction arises. And the contradiction is that the sequence 2 to the n over n is actually unbounded. If you look at something that we know is true from our assumption, is that n is strictly greater than 1. Therefore, 2 times n is strictly greater than n plus 1. Which means that 2 over n plus 1 is strictly greater than 1 over n. And if I multiply both of these by 2 to the n, we get 2 to the n plus 1 over n plus 1 is strictly greater than 2 to the n over n. So this is an increasing sequence of values, and because it's strictly increasing, that means that it's increasing without bound, which is really quite incredible. And it clearly shows that we have a contradiction here if we assume that 2 to the n is dominated by n. And we give an interesting corollary to this theorem that n is strictly dominated by 2 to the n. And that corollary comes about when we think about what happens to the logarithm of either of these functions. And the key thing to think about here is that because the logarithm, if a is strictly less than b, then the logarithm of a is also strictly less than the logarithm of b, because the logarithm is an strictly increasing function. And so the idea here is that what we've shown that for all n is strictly less than 2 to the n. So therefore, when we take the logarithm of both sides, we get log of n is less than logarithm of 2 to the n, which is log of 2 times n. And what we can clearly see is that function log of n is going to be strictly dominated by n as n gets larger and larger and larger. This is with witnesses k equals 1 and c equals log of 2 is the base of the logarithm. So this is very, very cool. Now the key thing to note here is that this logarithm can have any base that we want to give it. So it can be a general base b. If we choose a base b of base 2, because we're doing 2 to the n here, we actually get a very simplified expression. So if the base of the logarithm equals 2, then this constant c just becomes a constant 1, which is what is done in your book. However, we're going to see that different bases for actually expressions of numbers are going to be really important in computer science. So the idea here is that we always want to kind of think of how to deal with different bases, and this also allows you to deal with, say, the function 3 to the n, 5 to the n, e to the n, and actually show some of these properties for those functions as well. So the idea is that we want to continue on and introduce now some new general properties that are going to be very, very important. And I'll summarize these in the following theorems. If a function f1 is big O of g1, in other words, f is dominated above by g, F1, or F1 is dominated above by G1, and F2 is big O of G2, then we can say definitively that F1 plus F2 is big O of G. G is a specially constructed function. G is the maximum function of G1 and G2. And this also means in our other notation, the Hardy notation, that F1 plus F2 is dominated above by G. And the proof of this theorem is really rather straightforward. The main idea here is that we need to show that there exists a constant C and a constant K such that F1 plus F2 in absolute value is going to be less than or equal to this function G that we've defined right here. So we start the proof by assuming that F1 is bounded above by G1 and F2 is bounded above by G2, in which case we know that there exists K1, K2, C1, C2, such that for all x greater than K1, we have that absolute value of f of x is less than or equal to C1 times absolute value of G1 of x, and for all x greater than K2, we have that absolute value of f2 of x is less than or equal to C2 times G2 of x. And so we have then that if x is greater than k, where k is equal to the maximum of k1, k2, which are guaranteed to exist, we can look at the absolute value of f1 of x plus f2 of x. And we need to bound this absolute value now. Specifically, we need to find a c such that absolute value of f1 plus f2 of x is less than or equal to c times the absolute value of g. This is what we're trying to do. And the key thing that we're going to use here is what's called the Triangle Inequality, which is a basic, relatively basic inequality that will always hold. And there are many, many different important applications of this inequality and generalizations of this inequality. I'm not going to prove it here, but I encourage you to look up a proof of this. So I'll put on the side here that the triangle inequality in the form that we're going to use it is that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. So I highly encourage you to go through and look up proof of this. It's relatively straightforward and just uses algebra. This is for any two real numbers, a and b. This is less than or equal to absolute value of f1 of x plus absolute value of f2 of x both of which are bounded by, well, f1 is bounded by c1 times g absolute value of g1 of x plus c2 times absolute value of g2 of x. And this entire thing then is less than or equal to c1 plus c2 multiplied by the maximum of g1 of x or g2 of x in absolute value, which is the same thing as some constant c. This is our constant c, c1 plus c2 times the absolute value of the function g of x that we defined in the theorem statement. So this clearly proves our theorem. Because what we've shown is that there will always exist a k and a c such that g or f1 plus f2 is big O of g, where g is the max of g1 and g2, which are the functions that individual functions that bound f1 and f2. And an interesting corollary here is that if g1 of x equals g2 of x, which just then we'll call some new function h of x because they're the same function, then f1 plus f2 is big O of h of x, or f1 plus f2 is dominated above by h of x. So the idea here is that g1 and g2 are both bounded above by the same function, then their sum is also bounded above by that function. And now what we're going to do is we're going to go through and prove the theorem about products, which is, again, super useful. So this theorem is on products, and it's a very useful theorem. So we'll state this now. We have that if f is dominated above by g and h is dominated above by k, then f times h is dominated above by g times k. Remember, this is saying that if f is big O of g and h is big O of k, then f times h is big O of g times k. Furthermore, we have that if f grows at the same order of g, so f is bounded above by g and g is bounded above by f, and h grows at the same order of k, then f times h grows at the same order of g times k. Remember, this is saying that if f is big theta of g and h is big theta of k, then f times h is big theta of g times k. So this is, both these are super important, but we also have one more part of this theorem. We have that if f is strictly dominated above by g and h is just dominated above by k, then f times h is strictly dominated above by g times k. This has a couple different parts to it. Call them part 1, part 2, and part 3. I'm just going to go through and show part 1. Parts 2 and 3 are relatively straightforward. You have to prove a little bit more for 2 and 3, but they both depend on part 1 right here. For part 1, right, we have to assume that f is dominated above by g and h is dominated above by k, which means that there exists k1, k2, and c1, c2, such that the absolute value of f of x is less than or equal to c1 times the absolute value of g of x. This is for all x greater than k1, and for all x greater than k2, we have that h of x is less than or equal to c2 times k of x. So we choose k, the witness, to be equal to the maximum value of k1 and k2, and then we attain that the absolute value of f of x times h of x is going to be less than or equal to c1 times the absolute value of g of x, because the absolute value of a times b is always equal to absolute value of a times the absolute value of b. So this is the same thing as the absolute value of f times the absolute value of h, which will always be less than or equal to this times c2 times k of x. And then again, because of this equality, this is equal to c1 times c2 times g of x times k of x. Therefore, f times h is big O of g times k. And again, this is just a proof of part 1, but proof of parts 2 and 3 are relatively straightforward extensions of this idea. For this one, you have to show that really just kind of it's a very simple extension of part 1, because if f is on the same order of g, then f is bounded above by g, or dominated above by g, and g is dominated above by f, and so on and so forth for this one right here, for h. So you kind of have to apply the theorem from part 1 2 times for part 2. So it's a relatively simple extension. And same thing for part 3. It's slightly different extension, but the idea here is that you just got to use the fact that F is strictly dominated by G to show that, and the fact that H is dominated above by K to show that if these two things are true, then F times H has to be strictly dominated above by G times K. So this is a very important theorem, but this is also a relatively simple extension. I encourage you to go through and think about some of these extensions, because it's a good exercise to go through and kind of justify to yourself why this works. But the idea here is that with these theorems now, and we're going to have one more theorem a little bit later on, but with these theorems alone, we can go through and do a lot of different things. So we'll see some very important examples now of how to use this theorem and how it really simplifies these order of proofs and calculations. It's very, very straightforward and simple. I recommend going through and doing it yourself to show that the constant function 1 is strictly dominated by the function x. And we showed that any function is dominated above by itself by definition, because this is a reflexive relation. So by the previous theorem, we have that this implies that 1 times x is strictly dominated above by x times x. Or in other words, x is strictly dominated above by x squared. And it's a relatively easy extension to do a proof by induction. It really just amounts to, in the inductive step, of repeatedly applying the theorem from part 3 to get that for all n in z plus, the function x to the n is strictly dominated by x to the n plus 1. Which is going to be very important when we consider polynomials, which many algorithms have runtime of some order of a polynomial, which is very cool. For another example, we'll take something that we've previously shown, which is that n is strictly dominated by the function 2 to the n, and log of n is strictly dominated by n. Therefore, we can conclude from a relatively straightforward extension of part 1 that n times log of n will be strictly dominated by n times 2 to the n. Not only that, but it's relatively straightforward to rewrite n times log of n as log of n, and this log can be any base, log base b of n to the n, is strictly dominated by n times 2 to the n. And if we choose base 2, just for example, we can show that the function n to the n is strictly dominated by 2 to the power n times 2 to the n. So this is a function that grows faster than n to the n. And this really kind of shows that, in some sense, we can always kind of create a function that grows faster than any given function. So for the final theorem that I want to go through and show, is going to be very important as well. This is if f is the function g plus h, and g is, we'll say actually h is strictly dominated by g, then the order of growth of f is equal to that of the order of growth of g, or the order of growth of g plus h is equal to that of the order of growth of g. So f is big theta of g, which this theorem basically allows us to, in some sense, ignore lower order terms in sum. And it's in a similar mindset or similar idea to part 3 of the previous theorem. And so I'm going to omit proof of this theorem because it's relatively similar and straightforward. It's very, very similar to the previous theorems. It's a combination of the triangle inequality and a couple other ideas. And I want to do this in favor of going over a couple examples and specific applications of all of these ideas. So the first theorem that we'll give is that a polynomial of degree n has the same order as x to the n, or is we could say that p of n, that's the polynomial, is of the same order or has the same order as the highest term in the polynomial, or we could say that p of n is big theta of x to the n. And this is a super important theorem because polynomial orders appear all the time when we're discussing algorithms, which I'll give a couple examples of after this, which is why it's important to go through a proof of the theorem. And in our office hour sessions and the ALA sessions, there's a relatively straightforward proof of this that I gave for a couple different examples, but the proof extends generally, right, in general, and is covered in our book in detail. So I'm going to put that as method 1. This is the book proof. But using the theorems that we've done so far, we could even construct a different proof than the book does, because we have enough theorems at our disposal to really directly say the following. And I actually like this proof, method 2, better than the book's proof because it's a little bit more straightforward. However, I do expect you to know the book proof as well, so I would look at this theorem. And this is exercise 50 in the book. From chapter 3.2. So the easier way to prove this theorem is to use the theorems that we've already shown. Specifically, we've shown that xn will always be strictly dominated by x to the n plus 1, for the function x to the n, and therefore we can go through and use the theorem that I just wrote down to show that any polynomial, if p is a polynomial of the form x to the n, or Pn of x is a polynomial of the form an x to the n plus an minus 1 x to the n minus 1 all the way down to a1 times x plus a naught we can use induction to show that Pn of x is theta of x to the n, or equivalently Pn of x is on the same order as, grows at the same order as x to the n. The way we do that is by setting up the base case. This is for P1. And we know that A naught, or any constant, is strictly bounded by a1 times x. Therefore, a1 times x plus a naught is on the same order as a1 times x, which is on the same order as the function x. The inductive hypothesis is that there exists some n in the positive integers such that Pn of x is on the same order as x to the n in the inductive step is to show that for all n in Z plus, Pn of x is on the same order as x to the n, or if it grows on the same order as x to the n, then Pn plus 1 of x grows at the same order of x to the n plus 1. So we start by assuming that Pn of x is of the same order as x to the n. We know that Pn plus 1 of x is an plus 1 times x to the n plus 1 plus Pn of x and because Pn of x is on the order of x to the n, and an plus 1 x to the n plus 1 is on the same order as x to the n plus 1, we have that Pn of x is strictly dominated by x to the n plus 1. And because of this, and the theorem on summations, this means that Pn plus 1 of x is on the same order as x to the n plus 1. And if you want to be specific, it's an plus 1 times x to the n plus 1, but this constant an plus 1 does not matter. Therefore, for all n in Z plus, Pn of x is theta of x to the n, or Pn, the polynomial, nth order polynomial, is on the same order as x to the n. And this is a super useful theorem for a number of different reasons, but the big application here of all of this stuff is in computational complexity theory. There are two types of complexity: space complexity and time complexity of an algorithm. Both of these are essential when algorithms are implemented, but the idea is that we're just going to look at time complexity because space complexity is specifically tied to data structures used to implement the algorithm, which is a little bit more detail and complexity than we want to go over in this class. So we're going to restrict to time complexity.